Hello everybody. So in this video we're going to prove the third version of Hilbert's Nullstellensatz, which says the following. So once again we start with a finitely generated K algebra A, and the theorem says that the nil radical of A is equal to the Jakobson radical of A. So by definition this is the set consisting of all the nilpotence element of A. And this is also by definition this is equal to the intersection of all the maximal ideals of A. So before we begin with the proof, we're actually going to prove a proposition, which is more of a correlative of the first version. But okay, so the proposition says that if we have two finitely generated K algebras, let's call them A and B, and we also have a ring, a homomorphism of K algebras between those two things, so let's call this phi. Then the proposition says that the pre-image of any maximal ideal is again maximal, which is not true in general, because we know, for example, if we consider the ring homomorphism from the integers to the rationals, we know that this is not true. For instance, the trivial ideal is a maximal ideal of Q, but its pre-image, which is going to be the zero ideal, it's not a maximal ideal. Because the integers don't form a field. Okay, so let's see how this proof goes. So okay, so we start by defining a homomorphism. So I'm going to call him psi. So define psi going from A mod, going from this guy to B mod n. Right, and this is simply defined by taking an arbitrary element in here and just mapping it to phi of alpha mod n. Now one can clearly see that this is well defined, and that this is a ring homomorphism. But now the idea is to so we want to show that this is a maximal ideal. So what we will do is prove that this is a field. And we're going to do this by using a lemma we proved in the first version of the Nullstellensatz, which said that if we have a map between two integral domains and that map satisfies two conditions, namely if the map is injective and integral, then the lemma said that the first integral domain is a field if and only if the second is a field. So we're going to use that, which means that we have to prove that this map psi satisfies those hypotheses. Okay, so the first trivial remark is the following. So if n, since n is a maximal ideal, of course n is also a prime ideal of B, and this implies that its pre-image under phi it's also going to be a prime ideal, right? Which of course implies that this guy is this is an integral domain. Oops. Okay, on the other hand, n is a maximal ideal, which of course implies that it's also prime, which of course implies that B mod n is an integral domain. So we have a ring homomorphism between two integral domains. So the first thing we will prove is that this map psi is injective, right? And this is really easy. So if we have an element living in the kernel of psi, then this implies that its image is going to be 0. So this implies that phi of alpha is going to be an element in n, right? But of course this implies that alpha lives inside this pre-image, which of course implies that the element we started with, namely this guy, is equal to 0. So this implies that the kernel of psi is trivial, which implies that psi is injective. Okay, so the last thing we want to prove the last property we want to prove about this this map psi is that this ring is integral over this ring. But now, so what do? We now use the first version of Nullstellensatz. So the first version said that if we have a finitely generated K algebra, and that K algebra happens to be a field, then it's also algebraic over the field K, right? But now we assume that n is maximal, which means that B mod n is a field, and it's also pretty obvious that it is a finitely generated K algebra, since B is that. So this implies that B mod n is algebraic over K. But now it's easy to see that since this is algebraic over K, the same guy is integral over the ring, over this ring, right? Because every structure makes sense. I mean, A is a K algebra, so this is a K algebra. So if we have if every element of this ring satisfies a polynomial equation with coefficients in K, then it follows that it satisfies a polynomial equation with coefficients in this guy, right? But now we can use that lemma I mentioned, and the lemma said that now that we proved these properties of the map psi, the lemma said that if one of those things is a field, then the other one has also have to be a field, right? So since this is a field, we simply get that this is a field, which of course implies what we want, and namely that this is a maximal ideal, right? So this finishes the proof of this proposition, and I think we don't really need anything else to start proving the third version. So yeah, let me just move on to the next. So let me move to the third version, right? So we're going to prove that if A is a finitely generated K algebra, that we have this equality, right? So I mean, first of all, if we look at this inclusion, then this is trivial, because as we already mentioned, the nil radical of A is by definition is the set of all the nilpotent elements in A. But one can prove in basic commutative algebra that it's also, I mean, the nil radical can also be described as the intersection of all the prime ideals of A, right? And the Jacobson ideal is the Jacobson radical is the intersection of all the maximal ideals. So if something lives in every prime ideal, of course it's going to live in every maximal ideal, simply because every maximal ideal is prime, right? So this is trivial. So let's move on to the other inclusion, which is a bit trickier. So okay, so I want to prove that every guy in here lives inside the nil radical. So what I'm going to do is, so let F be an element in A such that F it's not an element of the nil radical, right? In order to be done, we just have to show that F won't live in the Jacobson radical of A, right? Okay. So the first idea is to consider is to localize with respect to this element, and since F is not an element of the nil radical, this implies that, well, if F was an element of the nil radical, then F to the power of n for some n greater or equal than 0 would be 0, right? But since F is not an element in the nil radical, what we get is that for every n greater or equal than 0, F of n is not 0, right? So this means that we can consider the localization with respect to F, right? So we just consider a F because if you recall, this is so we localize with respect to, so the multiplicative subset is all the powers of F, right? But by definition, we can't the multiplicatively closed subset cannot contain 0, right? So we have to make sure that every power of f is not equal to 0. So we can consider this guy, which is of course, so this is not 0, simply because, for example, 1 over f lives in this guy, right? But now we know, again, using basic commutative algebra, that every non-trivial ring contains a maximal ideal. Right? So now we define M to be alpha intersection with N. So the idea is to somehow prove that M is a maximal ideal and that F doesn't live in M. And then we're done, right? Since we want to show that F doesn't live in here, all we have to do is find the maximal ideal, let's call it M, it is going to be M, such that F doesn't live in M. Right, so we have to prove that M is a maximal ideal and that F, it's not an element in M, it's not an element of M. Okay, so first of all, it's easy to see that F is an ideal of A. This is trivial, I'm not going to write down the details. So the first claim is that F cannot live in M, right? Otherwise, so if F was an element of M, then F would also live inside N, right? And then we could just take 1 over F and we could multiply it by F, but now this is an element of the localization, and F is an element of N, right? This lives in here and this lives in N, and this is of course equal to 1, but now since N is an ideal, right, the product has to live in N. But this is wrong. This is a contradiction because N is a maximal ideal, right? And hence it can contain 1. Right. So we therefore have that F really is not an element of M. Okay. So what we have to prove, the last thing to prove, is that M is a maximal ideal. And how do we do that? So we consider a map. Okay, so we consider a map phi. We consider the natural map, right? Sending alpha to alpha over 1. So it's easy to see. So okay, so this is a ring homomorphism. Okay, it's easy to see that that if I consider the pre-image of N under this map, then this is exactly equal to, I mean, this is by definition this is this set, but now it's easy to see that this is just M, which is alpha A intersection with N, right? This is really easy. So since we know that N is maximal, all we have to do in order to show that M is maximal is to use the previous proposition. But the previous proposition assumed that we had 2 finitely generated K algebras, right? So by assumption, A is a finitely generated K algebra. So all we have to do is just prove, is to convince ourselves that this localization is also a finitely generated K algebra, right? But this is easy because, well, first of all, we have this map. I mean, we have a map going from K to A because A is a K algebra, and we also have this phi, right? So this implies that the localization is first of all a K algebra. But since, I mean, one way to look now, so we have to convince ourselves that this is also finitely generated, which of course, it follows from the fact that A is finitely generated, right? So if you want to convince yourself, just take a look at the fact that if I localize with respect to F, then this is exactly equal to this guy over here, which is by definition this is the A sub algebra of the localization generated by 1 over f, right? But now it's easy to see that every element in here, by using that fact that, I mean, if you consider the fact that A is a finitely generated K algebra, it follows that this guy has also got to be a finitely generated K algebra, right? And if you want to be explicit, if A is generated by, say, alpha 1, alpha n, so this guy is going to be generated by alpha 1, alpha n, and 1 over f as a K algebra, right? So in other words, what we have is that if I localize with respect to f, this is a finitely generated K algebra. And now we can use the previous proposition, right? And now if we use the previous proposition, we get that since n is maximal, its pre-image is going to be maximal, therefore m is maximal, right? M is maximal. And we're done, because as we already explained, we found a maximal ideal such that M doesn't live inside that, right? So this proves that F cannot be an element of the Jacobson radical, and we're done. This completes the proof of the third version of Hilbert's Nullstellensatz. And so I want to, so before we stop, I also wanted to prove a corollary. Maybe some people also call this this is another version of Hilbert's Nullstellensatz. But okay, so first of all, we have a definition that says that a ring A is said to be a Jacobson ring if every prime ideal is an intersection of maximal ideals, right? And the corollary says that every finitely generated K algebra, let's call it A, is a Jacobson ring, right? So in other words, every prime ideal of a finitely generated K algebra can be written as an intersection of maximal ideals. And in fact, we're going to prove that every prime ideal P is the intersection of all the maximal ideals of the ring containing P, right? So okay, so let P be an arbitrary prime ideal, right? So it's easy to see that A mod P is a finitely generated K algebra. Okay. Now, if we use the version of Nullstellensatz we just proved, we get that the nil radical of this ring is equal to the Jacobson radical of this ring, right? So this is maybe I should call this relation 1. But so this is a simple exercise. So so the nil radical of any so if I have A mod, I don't really need to have a prime ideal. If I have A mod I, where I is any ideal of my ring, then it's easy to see that the nil radical of this guy is equal to the radical of the ideal, namely P in our case, mod P, right? But this is equal to 0. This is 0 because every prime ideal is radical, right? And then for the radical of P is exactly equal to P. Therefore, we have P mod P, which is just 0. Thus, relation 1 implies that the Jacobson radical of A mod P is a trivial one, right? Therefore, by definition, this means that the intersection of all the maximal ideas of A mod P, this is trivial. This is the 0, right? And now I claim that this equality here implies the desired result, right? So it implies that P is going to be the intersection of all the maximal ideals in A, such that P is contained in M prime. Okay, so how do we prove this? So first of all, if if I have an element that lives in P and I consider an arbitrary maximal ideal M prime containing P, well, of course, this element is also going to live in M prime, right? So the fact that this is a subset of this, it's trivial, right? So let's try to see why the other inclusion is true, right? Okay, so the point here is to okay, so we have this map, let me call it again phi. Okay, so we have this map, right? The natural map is just setting alpha to alpha mod P. So here we have to recall this basic fact from commutative algebra that says that so if we look at this ring homomorphism, we have this bijection between the set of the prime ideals, the set of the ideals of A that contain P and the ideals of A mod P, right? And this bijection, for example, respects preserves maximal ideals, right? And it's given by, so if I give you an ideal I that contains P, then you just map it to I mod P, which is easily seen to be an ideal of A mod P, because I is an ideal of A, right? So if I have, so if X is an element, okay, let me call this intersection B. So if X is an element in B, right? So if X lives in every prime ideal that contain, in every maximal ideal of A containing P, then under this bijection we just mentioned, we have that phi of X, when phi is this map, is going to live in every maximal ideal of A mod P. Right? But as we saw, this is just equal to 0, right? Which means that X, so phi of X has to be equal to 0, which means that X is an element of the kernel of phi, but the kernel of phi is exactly equal to P. Therefore, X has to live in P, and we're done, right? We showed that we have this inclusion. Therefore our arbitrary prime ideal is an intersection of maximal ideals, right? And this proves that every finitely generated K algebra is a Jacobson ring. So thank you for watching, and I'll see you in the next video where we're going to prove the fourth version of Nullstellensatz. Thank you for watching.